Hi, in this video, we want to take a look at log linear models and modeling with Poisson regression. Okay, so what we're going to be doing, we've got a table, and on that table, we have counts. And then marginally along the table, each dimension corresponds to a variable. And we're going to be using Poisson regression, where the count is a target variable, and the marginal dimensions correspond to predictor variables. All right, so let's go ahead and take a look. We're going to start with a 2x2 table, easiest example possible, then we'll move on from there. All right, this example is taken from Generalized Linear Models with examples in R. It's a Springer textbook. It's free to download from the UCF website, or excuse me, UCF library. And the main thing that's modified is that I've changed all the code to be more along the lines with how I code. So something I always do, for example, you'll notice that when I open up online, I close at the same indentation every single time. Also, every parameter, every named parameter, I should say, gets its own line inside function calls. And so those are the two main things. Also, I have a different naming convention. At work, I spell it out. I always spell it out. I find that helps me so much when I go back to look at my old code to figure out what did I do 6 months ago, when I need to reuse my code. All right, so for this example, we've got some counts. We got 4 of them because we got a 2x2 table. And then one variable is attitude. It's either for or against, that's a factor. And then we have income, high or low. And so we can put these 3 things together into a data frame, and we get this data frame. All right, so this format is a good format for like Poisson regression as is. So, but let's go ahead and change this into something that's more similar to a log linear model. All right, so here, I'm going to take the xtabs function, so that's cross table is what xtabs stands for, cross table. We're going to say that count is what's on the table, and then my dimensions are going to be attitude and income. And this can handle higher dimension tables, but here it's a 2x2, it's flat. It can be represented on a 2-dimensional surface. So this is what we get. All right, you'll notice that attitude is first, and then income is second. And here attitude is rows, income is columns. So remember, when I talk about a matrix is always rows, then columns, just like we have here. All right, well, let's go ahead and let's build a Poisson regression model. And I'm going to use this data frame as is. All right, so I'm going to use the generalized linear model function. I'm going to take my formula, attitude plus income. Here is the data, and the family is Poisson. Okay, so this is what it says it's Poisson regression. I have to specify the family. If I don't specify the family, R is going to treat it as Gaussian standard multiple linear regression. Okay, now you'll notice that I'm not specifying the length function. With Poisson, the default is the log length function. We also have the option of square root or identity. I feel like if you don't know, go with the default on this one. Now, I want to do a hypothesis test. Is this a useful model? I would like to know. I want some information. I want some verification of, should I launch this model? Should I chuck it in the bin? What should I do with it? So let's go ahead and run ANOVA. Now, remember, when I'm doing generalized linear models, I usually do not have an F statistic to generate. All right, so I don't have the whole sum of squares like structure that we have with multiple linear regression. I need something else. So I don't have the F distribution, but we have a chi-squared distribution to work with. So what I'm going to do, I'm going to, inside ANOVA, I'm going to set test equal to chi-squared for this. All right, so this line here, all right, well, let me back up. Terms are added sequentially, first to last. All right, what that is saying is that this test, this hypothesis test, is saying, hey, should we add attitude to the constant model? All right, yes or no. The alternative is add it. The alternative is don't. Now here, this is saying, should we add income to the constant plus attitude model? And it just keeps on going down. It's like the top line corresponds to the most simple model. Then the next line is from adding the first predictor, then adding a new predictor, adding new predictor, adding new predictor down the list. So if I had 5 predictors, I would have null, then the first, second, third, fourth, fifth. And each time the line represents the hypothesis test of should I add the new predictor. All right, and we can look at the coefficients. So remember that this corresponds to an exponential. So it doesn't have the same structure as a regular degree 1 polynomial like we're used to with multiple linear regression. All right, so one thing that I find is a good thing to do when I start working on these types of problems, it's hard to understand, like, what is it I'm actually looking at when I get my output? Like, what does this tell me? Well, one thing that I can do, and I feel is a good course of action, is to run the predict function on your distinct observations values. So I take all my observation predictor variable values, I drop those into the model, run a prediction, and I see what is the modeled expected value. And remember, when I do this, I want to set it to response, because if I don't, what it's going to do, it's going to give me like the link function version of what's going on. And that's not what I want. I want actual numbers on this. All right, and so we can see here's the output. So yeah, do these numbers seem reasonable? Let's take a look. Originally, I had 263, 258, 151, and 222. All right. And not a perfect fit, but it's pretty close. So something to think about, though, is that how many distinct predictor variable values do I have when I talk about the total observations? Well, I've got 2 levels for income and 2 levels for attitude. That means I've got like 4 distinct predictor variable values. Well, how many parameters do I have in this model? I have the intercept, I have coefficient of attitude against those, and I have the coefficient for income low. I've got 3, yet I only have like 4 observations for modeling. That's, I mean, this is pretty highly fit onto there. I'd have to have a lot of faith in, like, in my prior understanding of the situation for me to use this model. All right, so now what we can do, let's go ahead and take a look at what would happen if instead of just having attitude and income, we have attitude, income, and an interaction term. So here, it's similar as before, but I'm going to have attitude, interaction, income in the model tacked on. And once again, I'm going to run a chi-squared test. And we can see that it looks like attitude, is worth adding in, and then income is worth adding in, and then attitude, interaction, income looks like it's worth adding to the prior ones. All right, so I feel like this might not be too bad of a model. And let's look at the coefficients. I always like to compare them to the prior. So attitude against is negative 0.3, negative 0.5, all right. And then income low, 0.15. All right, a little bit of a difference there. And the intercept is 0.56, and not too far off. All right, so bit of a change on this one, and this is new. All right, so now let's do the prediction. Now, when I look at this, I've got 263, 258, 151, and 222. Let's take a look at what we had previously. 263, 258, 151, 222. Huh. It's a perfect fit. Why is that? Because I have 4 distinct predictor variable values and I only have one response variable for each one, and I've got 4 parameters. It's going to be a perfect fit. All right, so now I can run a prop.table. What this does, this computes, this looks at the conditional probability for me, that if someone has, if they are high income, I can see that they modeled likelihood of being 4 is about 2/3. If they have high income, modeled probability of them being against is about 1/3. So this is given that they are high income. This gives me the probability, the likelihood. This is the modeled likelihood of 4 and against. If they have low income, this gives me the conditional modeled likelihood of 4 or against. It looks like it's about 50-50. Here it looks like it's 2/3, 1/3. All right, so now let's do another example, but this time we want to do a 3-dimensional table example. So let's go ahead and load some data. So I'm using the KLMS data set package, and we kidney stones. Okay, so our data set, we have the situation on the stones for size, small or large, method of treatment, and then the outcome. All right, what we want to do, we want to model like what's going on. So somebody comes to us as like we're, maybe a physician or we're a biostatistician, and someone wants to choose the best course of action for treating somebody with kidney stones. And they have methods A and B, and they can see that the patient has either small or large kidney stones. And they want to know which method is the better choice. Okay, so and now here we're only going to look at the outcome. We're not going to look at side effects or cost or anything like that. We're just looking at effectiveness. All right, so let's look at a couple of different models. First type of model is mutual independence. Here, mutual independence, you notice I have no interaction terms whatsoever. All right, so I'm going to be storing all these models in a list. I'm going to call all the generalized linear models, I'm going to store in the list GLM. And then mutual independence, no interaction whatsoever. Next one, let's take a look at partial independence outcomes. So here, size and method are not independent of each other, but here we're modeling that outcome is independent of the other 2 variables. Here for partial independence, we're saying that method is independent of the other 2. And here in this one, for partial independent size, we're saying that size is independent of method and income. So size is independent of the other 2. So when they're not independent, when 2 variables are not independent of each other, we're going to be using an interaction term between them. All right. Now here, we're interested in conditional independence. For conditional independence, we're going to have interaction, but it's going to be method plus outcome with size. So here, what we're saying is that method has conditional independence of outcome, and outcome has conditional independence of method after size has been established. So if I know what size is, then from that point on, method and outcome are considered independent of each other. Now here for conditional independence, method, I'm saying that once method is known, so if I know the condition of the value of method, then after that, size and outcome are independent. For conditional independence outcome, once I condition on a known value of outcome, then size and method are independent of each other. Now, uniform association. Now here, this situation is where we have 2-way interaction between all variables. We have degree 1 terms all the way across. So all 2 are not independent of each other, but we do not have a 3-way interaction when we do uniform association. And saturated, saturated means we have as many predicted variables as we can squeeze out of this, and we have all degree 1 terms, all 2-way interactions, all 3-way interactions off of this. All right, so now I want to take a look at the output. I'm just going to print the list. So I've got everything stored, all these models are stored nice and neat in one list together. This makes my workspace nice and clean and tidy so I can work through things pretty quick. And I can go through and I can take a look. I've got all of these different models. It's a lot to look at and it's a lot to wade through. At this point, I'm really not going to be worried about the particular values. I'm worried about finding what model is the best model, which model fits the data. Now, the classical statistician way to approach this is to say that I need to know subject matter so well that I will have like a preconceived notion of what the model should be. That's definitely the better way to go if your subject matter expert is correct. My personal experience is that a lot of subject matter experts will give you information that contradicts your data. And so then you're in the weird position of, or I look at the data and the data says one thing, the subject matter expert says one thing, trying to find that balance, because you don't want to reduce, you want to release a solid model, you know, given the data, but you also want to have a model that jives with the subject matter expert. So you have to work on it. All right, so now what I want to do, I want to run that chi-square test on all these models. Now, what I could do, I could write the code over and over and over and do it. But you know what I'm going to do? I'm going to be lazy. I've got everything all in a nice, neat list. So what I'm going to do, I'm going to pull the lapply function. What this is going to do, this is going to take the entire list and it's going to apply this chi-squared test to every single model in this list. And it's going to do it automatically for me. It's going to be beautiful. All right, so I'll look through and size and method and then outcome. It's a lot to look at. Let's see. Notice that method is not statistically significant on this. Something, you know, we get a similar result. And what we want to do, we just want to like individually look at these step by step, try to get an impression of what's going on. Notice that method and outcome together is not statistically significant for adding, given that. And then adding these two do not improve the model by the standard. Okay, so now, that's a lot of hypothesis testing, and that's a lot to wade through. So I'm thinking this may not be the best way to go because I have to interpret model after model after model, and I have to interpret each additional step in the model building process, which is kind of hard to keep it all straight. So what I'm going to do to try and make my life a little bit easier, I'm going to use sapply to get the Akaike's information criterion off of each model. And then I'm going to go ahead and just sort it to see what looks good to me. Okay, so when I do this, I see uniform association and conditional independent size have the smallest AIC. So remember, AIC is something I want to have small. Mutual independence, that's pretty large. It's much larger than these two. So, you know, the saturated model is surprisingly low. That really surprised me. Conditional independence method, all right. But right now, I'm leaning towards conditional independence size, or maybe uniform association. So let's go ahead and scroll up, take a look. So I want uniform association and conditional independence size. Let's see, where is it? All right, so here we've got conditional independence size, and we can see that it goes size, method, then outcome, and both of our interaction terms are are really carrying their weight in the model. In uniform association, here we have all two variable interaction terms. So this is very similar to the previous one, but method outcome is tacked on, but that's not statistically significant. So I might not want to put that one on there. And then the saturated model wasn't too bad by the AIC criterion, but these interaction terms are not statistically significant. So I am leaning towards the conditional one with size. All right, so let's scroll back up to that. Let's take a look. We want conditional independence on size. I want to go all the way up to the original call. I mean, that's a lot of scrolling. All right, so in this model here, what we're doing, we're saying that after size is established, so large or small, so after size is established as large or small, method and outcome are independent of each other. Okay. So, at least when it comes to the counts. So let's think about that. So that means that so after I break it up, method and outcome, think about that for a moment. What is that going to mean for us if outcome is independent of method? All right, so now let's take a look at some more aspects of this. All right, so what do we conclude by this? What we want to do, when I look at this data, I actually want to break up that three-dimensional table by size. I want to take all the data that is size small. I want to take all the data that's size large. And now it's two separate populations from my point of view. So when I run my analysis, I want them to be separated from each other. All right. And so let's go ahead and make a cross-tabulation table. So the wrong way to collapse this, because we know that size is really important on this, I do not want to collapse my data in this manner. You notice what I've got here? I've got method and I've got outcome. Do I have size in there? Well, what we just showed a moment ago is that size should definitely not be marginalized out. Size is definitely something critical, something important. If I look at the proportions, if I look here, I can see that using method A is going to have success about 78%. Method B is going to have success about 83%. That's overall, not considering size. But this is the wrong way to do it. Notice I put the word incorrect in this. This is the incorrect way to collapse the data. This is not the way we want to infer off of this. If I look at this, I'm going to go, hey, B is the better way to go. It's not a big difference, but if I was having problems with kidney stones, I would want that 5% improvement on my treatment. But if we instead break up the data in the correct way, if I look at it this way, I say, all right, let's go with large. I break it up. Then I've got A, 2773, B, 3169. All right, those are pretty close to each other as far as the proportions are concerned. Small, we have 7% and 93%. Here we have 0.13 and about 87%. Okay, now let's think about this for a moment. If I look at this, success was 78.83. Here it's 73.69. And here it's 93.86. All right, so these numbers are deviating quite a bit from this one right here. So if I want to go with the overall numbers using if I want to go with the overall numbers, not considering size, I'm really losing out a lot of information because here success is 93%, here success is 73%. That's a big difference. Now, if I look at these numbers, these aren't that far away from each other. These numbers aren't that far. These numbers aren't that far. These numbers aren't that far. And these numbers aren't that far from each other. What does that tell me? Method really doesn't matter. Really, the outcome is dependent on the size of the stone, not the method chosen. Now, either way, like here, you can see that method A is a little bit better. It's not a huge difference, but I mean, if I was the one with the stone, I would want that. I would want to go with A instead of B. Here, 73, 69, not a big difference, but once again, A is better. So when I look at this, if I collapse the data incorrectly, I would say B was the better choice. But when I break it up properly, I can see that A is the better choice either way. And furthermore, I see that honestly, it's the size of the stone that dictates outcome, not the treatment selected, more than likely. All right, so if I'm doing a counting problem and the primary non-count variable of interest is binary, we can use logistic regression instead of Poisson regression. All right, so the situation that where I can go back and forth on this is if I have a large population and a small probability of like success in terms of Bernoulli distribution. If I'm in that situation, then logistic regression or Poisson regression will give me about the same results. I should do whichever one is easiest, whichever one is simpler, or whichever one my audience will accept most readily. Something about if I want to do logistic regression, remember I have to have a number of successes and a number of failures to fit that model. If I'm doing something like that, then I have to have an idea of what the population size is. You know, so if I was doing like disease cases in a city, well, if I don't know the exact population of the city, but I do know the number of cases of the disease, then I really can't count the number of like failures from a Bernoulli point of view if I don't know the population of the city. But the Poisson distribution, I don't need to know that. So this is a good way to go. All right, so if we do this, so I want to use logistic regression, so binomial distribution, and I'm going to do it on that GMO data that this video started with. So, generalized linear model formula is that attitude depends on income. My data is the data from way back there. Now here is the kicker. The weights are the counts. And that's how I'm incorporating counts into this. Now something about this is I have to have like everybody accounted for in some way, shape, or form to be able to do this. I have to have a number of people that are successes and a number of people that are failures in a Bernoulli sense to be able to run this. And then I can run ANOVA with a chi-squared, just like we have been. It looks like we got a pretty good model. Yeah, I'm convinced. All right, now let's do this for kidney stone data. Now, what I'm going to do on this one, I'm going to do pretty much the same thing as I was just doing, except I'm going to go through and I'm going to manually remove terms to get down to a simpler model. So I'm going to start with interaction, size, and method. And then when I do ANOVA, I can see that the interaction term is not statistically significant. So I'm going to go ahead and get rid of the interaction term. And this confirms that I should remove interaction. All right, so now let's go ahead. I'm going to rebuild the model, but this time I'm going to use size and method. And this is on the kidney stones data we looked at a moment ago. And I'm going to do the chi-squared. I see that method is not statistically significant. So let's go ahead and remove that. And this confirms that method, it's a good idea to remove method from here. All right, so now after I remove interaction and I remove method, I'm down to just the size. All right, well, let's look at my model. Well, hey, that's statistically significant, right? And the intercept and the slope are statistically significant. So it looks like I have the right model. So you'll notice that with Poisson regression, the log linear model, or with logistic regression, I conclude that the same model should be used. Now, a lot of the statistics, a lot of the values will be slightly different because of different methods of fitting, different methods of measuring quality. But largely, globally speaking, you're going to get similar results either way. There will be a difference, like there will be things that change if, like the order of removing prediction variables, stuff like that. But largely, they're going to look pretty close. All right, now for this next part of the video, I want to look at higher order tables. All right, so I want to look at depression youth data. And here we have age, group, gender, and depression. And we have the number of observations. So we have age, group, gender are all covariates to depression. And we have counts. All right, so the author of the textbook chose age, depression, gender to have a three-way interaction, and age and group to have a two-way interaction. And you notice I'm just running it, and I'm using the count as the target variable. And here is the model. I honestly would have probably removed group for this, or at least considered it. I personally would have liked to reduce it down so that you only have one non-statistically significant, term in the hypothesis testing, but yeah, whatever. Okay, so let's take a look. So I notice if I look up here, I've got age with depression, gender. I've got age with group. So age is definitely an important one. Let's go ahead and split it up by male and female. Okay, so when I look at here, I see that I have, this is the female part of the data. The age is going this way. So depression high, we can see that the depression is at, by this measurement, depression is at its worst in years 12, 13, and 14. Gets a little bit better, ages 15, 16, and then drops off substantially 17, 18. So as time goes on, things get better for the girls. Now for the boys, we can see that the boys, well, they have a more constant range. We either have 0.1 or 0.12 as the percent of high depression. So it's a more narrow range of values. But we see also that it stays relatively constant. Like age may not be impacting male depression, and while age is probably a bigger factor in terms of female depression, according to this data. All right, that's all I've got for you. Take care and goodbye.